Section A, fractional exponents.
Sometimes when you're dealing in the realm of exponents, they come to you in the form of fractions. When this happens, you gotta know how to deal with them head on and show them who's boss. Here's how.
We're going to prepare ourselves by taking a look at the formulas for fractional exponents, because they'll be a good tool for us to do battle with. So, let's take a look at these letters, then we'll stick in some numbers.
The first form for fractional exponents looks like this. A base number a raised to the 1 over n power, where n is a positive number. So, we might have something like 3 to the 1/2 power. When we've got a number with an exponent that's a simple fraction, like 3 to the 1/2 power, it just means the square root of 3. We look at what number is in the denominator and take that root of our base number.
So, in the same way, 3 to the 1/3 power means the cube root of 3. 3 to the 1/4 power means the 4th root of 3. 3 to the 1/5 power means the 5th root of 3, and so on.
Now, what happens if we've got the same kind of exponent, except now it's negative? Well, we've got to do things just a little different. We've got to take the reciprocal of the base number and then make the exponent positive.
The reciprocal of a number is 1 over that number. The reciprocal of 5 is 1 over 5. Check out this next item.
Let's say we have 8 to the negative 1/3 power. The rule says we can take the reciprocal of the base number, giving us 1 over 8, and make the exponent positive. So we get 1 over 8 to the positive 1/3. We know that the 1/3 power also means the cube root, so we get 1 over the cube root of 8. But we're not quite done because we can take the cube root of 8 and simplify it to 2. So, when all is said and done, we've got 1 over 2, or 1/2.
So, we just want to take the reciprocal of our base number and make the exponent positive. Then we simplify it if it's necessary. Let's do a couple more for practice.
If we've got 3 to the negative 1/2, first we take the reciprocal of the base number by placing 1 over 3. Next we make the exponent positive. Now we've got 1 over 3 to the positive 1/2 power. Again, because we've got a 2 in the denominator of our exponent, we take the square root of our 3 here. So we end up with 1 over the square root of 3. Since the square root of 3 is not a perfect square, we just leave this as our answer.
Finally, if we look at 2 to the negative 1/3 power, our first move is to take the reciprocal to get 1 over 2. Then we make the exponent positive, and we've got 1 over 2 to the positive 1/3 power. Next, we take the cube root of our bottom number, 2. So, our answer is 1 over the cube root of 2.
Notice anything similar in all the exponents we've done so far? They've all had 1 in the numerator. That makes a pretty clean deal. But what if we had a numerator where the number was something other than 1? What do you do?
Well, when we have a fractional exponent where the numerator is not a 1, we have 2 easy steps. We raise the base number to the power of the numerator and then take the root as signaled by the denominator.
Requesting permission to raise the base number to the numerator. That's the base number to numerator. Come in, ground.
Roger, base. We are now raising you to the numerator. You are now fully raised. Just waiting now on the denominator. The denominator should transform into the root at any moment now. Oh, there it goes. There it goes, ladies and gentlemen. The denominator has signaled which root and...
Ground, can we go over that again?
Roger.
Roger, let's look at that again. Say we have a number like 4 to the 3/5 power. Now stay with me here. The numerator of the fractional exponent, 3, is going to become the exponent for the base number, 4, so we get 4 to the 3rd power. Notice we replace the 3's spot in the fraction with the number 1. Remember how we learned to use the fraction 1/5 to take the 5th root? So, we do that here and take the 5th root of 4 cubed.
But our answer can still be simplified. See how we've got 3 4's under the radical? Well, we know 4 can be broken down into 2 times 2, so let's do that. When we break our 4's down, we've got 6 2's under the radical. Now, we're ready to take the 5th root, which means we take a single 2 and bring it outside the radical, leaving 1 2 underneath. That signifies that we've taken 5 2's from under the radical, or the 5th root. When all is said and done, we're left with 2 times the 5th root of 2.
What if we had 4 to the negative 3/5 power?
Well, if we had 4 to the negative 3/5 power, remember, the only thing we do differently is our first step. We've got to take the reciprocal of the base number first and make the exponent positive. We get the reciprocal by placing 1 over 4 and then make our exponent positive 3/5. Now our steps are the same. We raise our 4 to the 3rd power and take the 5th root of that. Next we simplify, so we've got 1 over the 5th root of 4 times 4 times 4, which breaks into 2 times 2 times 2 times 2 times 2 times 2. Then we take the 5th root, which gives us 1 over 2 times the 5th root of 2.
Let's do one more example where our exponent doesn't have a nice, neat 1 in the numerator. Take a look at 2 to the negative 2/5 power.
Our first step is to take the reciprocal because of the negative exponent. Then we get 1 over 2 to the positive 2/5 power. Next we use the numerator of the exponent, 2, and raise our base, 2, to the 2nd power. Remember, when we take that numerator, we put a 1 in its place. Now we take the 5th root of 2 squared, or the 5th root of 4. Since we can't take the 5th root of 4 evenly, we're going to leave it as is. That means our answer is 1 over the 5th root of 4.
So that's how we handle fractional exponents. It's really not that hard to deal with them once we get the rules down. Now let's take a little time to do a playback of part 4, our fun with fractional exponents.
A fractional exponent with the 1 in the numerator means we can take the root of the base number as signaled by the denominator. If we've got a number that isn't a 1 in the numerator, then we have to raise our base number to the numerator and then take the root as signified by our denominator. And finally, if we've got a negative fractional exponent, we take the reciprocal of the base number and proceed with the usual steps. Raise the base to the numerator and use the denominator as the root.
Now that we've done all that good exponent stuff, we're going to look at something a little different. We're going to take a sizable step closer to the world of algebra. Let's go!
Part 5, Inequalities.
All right, when we're talking about inequalities, we're talking about mathematical statements that are unequal. They have two sides that don't balance. So store that away in your brain bank, because before we get into the thick of inequalities, we're going to look at some different kinds of numbers and how they fit on a number line. This will set us up for our work with inequalities.
Section A, Numbers and Number Lines.
If you remember back to the beginning of the program, we talked about integers like 0, 1, 2, and 3, and negative 1, 2, and 3. And we've also talked about fractions. All these numbers are called rational numbers. What's that?
Well, a rational number is just a number that can be expressed in fractional form. 5 is a rational number because it can be expressed as 5 over 1. 17/35 is also a rational number because it's already in fractional form. And now that we know what rational numbers are, the time has come for us to explore new lands.
Just like we have rational people and rational numbers in this world, we've also got irrational ones. Irrational numbers are decimals that go on forever and don't repeat.
An example of an irrational number would be the number pi. We often see it listed as this symbol, which is the Greek letter pi. Pi represents the ratio of a circle's circumference to its diameter. But don't worry yourselves with that right now. What we want to focus on is the numerical expression of pi, which is 3.14. We usually use 3.14 as a value for pi, but this is actually rounded off. Pi really goes on and on forever. We just round it off to 3.14. Its decimal representation never ends and it never repeats. That's why it's an irrational number.
Another example of an irrational number is the square root of 2. The square root of any number that is not a perfect square is an irrational number. They're irrational because the decimal representations just keep going and they don't repeat. They just refuse to give up.
Now, there are numbers that go on and do repeat. These are called repeating decimals. A repeating decimal is a rational number. An example is the fraction 1/3. If we tried to divide this out, we'd continue to get 0.33333. Notice the repetition of the 3. This would go on forever. Same with the fraction 23 over 99. If we divided this out, we'd continue to get 0.23232323 forever.
Forever is a long time. So both a repeating decimal and an irrational number go on forever, but the non-repeating decimal is an irrational number while the repeating decimal is a rational number. Now, a good thing to know about all the numbers we've been talking about so far is that they all fall under the big old heading of real numbers.
I am real. This is real.
That's right. And whenever we've got a real number, we can put it on a number line. We used number lines a little while back in the absolute value section. Remember, a number line looks like what it sounds like it looks like. It's a line with a bunch of ordered numbers. We can use this number line to express certain mathematical statements, or just to identify a particular number.
Whenever we have a number line, 0 marks the division between the positive and negative numbers. All of the positive numbers are to the right of 0, and all of the negative numbers are to the left of 0. The arrows at the end of the lines mean that each end goes on and on forever.
Now here's the freaky thing. Number lines even include irrational numbers. Remember we said the square root of 2 was an irrational number? Well, it still is. And it's easier to figure out where it goes on the number line if you convert it into a decimal first. So you may have a chart in your book or a calculator that shows you the square root of 2 is approximately 1.41 when we round it off.
When we look at it this way, we see that 1.41 is close to 1.5, which is the halfway point between 1 and 2. We usually make an estimate, or a guesstimate, when we're putting irrational numbers on a number line. So on the number line, the square root of 2 goes just a shade to the left of where we'd find 1.5, and we put a little marker. We need to label the point since it doesn't fall on a whole number. Right here, we're going to write in the square root of 2, so anybody else who looks at our line can know what number we're talking about.
How about a number like 2.5?
We know that 2.5 is midway between the whole numbers 2 and 3 because it just means 2.5. So this is where it goes on the number line, right smack dab in the middle between 2 and 3. Make sense?
Mm-hmm. How about a negative number?
Say we have a negative 3.4. That means we have a number that is smaller than negative 3 and larger than negative 4, which means that our point would go right here on the number line. Notice that negative 3.4 is bigger than negative 4. The numbers to the left are less than the numbers to the right, which means the further left we go, the smaller we get.
It may seem a little funny, but if you're confused, don't call the math helpline just yet. We're going to get into some more details. Let's get into inequalities.
Section B, putting inequalities on the number line.
An inequality is a mathematical expression that is unbalanced. Statements like 5 is greater than 3 or 4 is less than 7 are considered inequalities because the two sides don't balance. Here's an example of what we're talking about.
Suppose you and your friend are on a teeter-totter, and neither of you are pushing with your feet. If your weights are equal, then the teeter-totter would be straight across like this. Now, if your friend got off, you'd go crashing into the ground. Now your weight is greater than the weight on the other side, and that means the teeter-totter is unbalanced.
Now, if your other friend, Big Bruce, decides to come and get on the other side, you're going to go soaring back up. Now the teeter-totter is unbalanced again, but this time it's unbalanced the other way. So, we say that your weight is less than Big Bruce's.
Let's go over the symbols we use when we're working with inequalities. Whenever you see this symbol, it means less than. So if you see something like this, it means 3 is less than 5. It's kind of like an equal sign, except 3 doesn't equal 5, it's less than 5. We use this wedge-shaped symbol to indicate less than. See how when we straighten this wedge out, it looks like the letter L? When you come across this symbol facing this way, you can remember that it looks like an L, which stands for less than. So here, 2 is less than 7.
Now, if you see the symbol facing the other direction, then it means greater than. So this would be read, 6 is greater than 2. Likewise, 9 is greater than 8.
Less than, greater than, less than, greater than, less than, greater than.
Now, you can remember which way to face the symbol if you use this little trick.
Think of your symbol like the mouth of a big, hungry, number-eating dinosaur. Your dinosaur is always going to want to eat the bigger number, even if he's already had lunch. So the dinosaur's mouth will always be going for the bigger number.
Now there's one more little piece to this inequality puzzle. Sometimes the greater than or less than signs can have a line underneath them.
When you see the less than sign with a line under it, it means less than or equal to. If you see the greater than sign with a line under it, it means greater than or equal to.
So when we see something like this, which means 3 is less than or equal to x, or this, 9 is greater than or equal to x, you might be noticing that we really haven't dealt with the x's before. But at this point, just know that these x's here are like the other letters we've seen. They're kind of like stand-ins. They simply represent some number, or numbers, that would fit correctly into our mathematical statement. So in our first inequality, x could have any value higher than 3, or x could equal 3 itself. In our second inequality, x could equal 9, or anything less than 9.
Alrighty then. With that knowledge under our belts, let's talk about intervals. Interval is a word we use when we want to talk about all of the numbers between two other numbers, or greater than one number and less than the other. So, if you see this notation, parentheses 4, comma 8, parentheses, this represents all numbers between 4 and 8.
When dealing with intervals, we come across two different ways they're written. There are parentheses like these, and brackets like these. Each has its own meaning.
Kind of like signs in baseball.
With intervals, the left parentheses means greater than, and the right parentheses means less than. This is called an open interval. If we've got brackets, the left bracket means greater than or equal to, and the right bracket means less than or equal to. This is called a closed interval. The numbers inside these symbols should be separated by a comma. The first example we looked at was the open interval bounded by 4 and 8. We know it's open because it's got parentheses. This can also be written with inequalities like we did before. It looks like this. X is greater than 4 and less than 8. That means we've got the interval of all numbers greater than 4 and less than 8. That X you see simply represents the phrase all numbers. Therefore, our interval includes the integers 5, 6, and 7, and all numbers in between, like 5.22 and 6.11. But it doesn't include 4 and 8 themselves.
Now, if we saw this, bracket, 0, 3, bracket, we would know that it meant the interval of all numbers between 0 and 3, including 0 and 3. It can also be written like this, which means x is greater than or equal to 0 and less than or equal to 3.
Now, just like we can go to our closet and slip on one ice skate and one roller skate, we can also mix up brackets and parentheses. Take a look at these dicey combos.
We could come across something that looks like this, bracket 3, comma 6, parentheses. Now remember that the left bracket means greater than or equal to, and the right parentheses means less than. So our interval would translate into all numbers greater than or equal to 3 and less than 6. Remember, we can also write it this way, with the corresponding symbols and numbers on either side of the X. Okie dokie. I think we're ready to put some of these on a number line.
Say we've got the interval of -2 and +2. Remember, what this really means is all numbers greater than -2 and all numbers less than +2.
This just in. When we put inequalities on number lines, we use an open circle to mean greater than or less than, and a filled-in circle when the interval includes the phrase or equal to. To recap, open circle for greater than or less than, filled-in circle when we've got or equal to. Now, back to our example.
Because we've got an open interval, we put an open circle at -2 and an open circle at +2. We do this because we're only dealing with less than and greater than signs, not equal to. Next, we shade the line in between them. Now, the shaded part of the number line represents our interval between -2 and +2, but not including -2 and +2.
Let's do another one of these. Check out parentheses 0, 3, bracket, or x is greater than 0 and less than or equal to 3.
On the number line, we put an open circle at 0 and a filled-in circle at 3. See, now we've got a closed circle at 3 because we're dealing with a right bracket, which means less than or equal to. Then we shade the line in between them. This means the shaded part of our line represents all the numbers after 0 up to and including 3.
Okay, let's do one more of these puppies just to make sure we're on the same wavelength. Take a look.
we've got bracket -1, comma, +1, parentheses. This means x is greater than or equal to -1 and x is less than +1. It maps out like this. We've got a filled-in circle at -1 and an open circle at +1. The line in between is shaded.
All the intervals we've looked at so far have been what are called finite intervals. They're considered finite because the length of the intervals are finite, meaning we can measure where they begin and where they end. For example, the interval bracket 1, comma 4 parentheses starts at 1 with a filled-in circle and ends at 4 with an open circle. Notice it starts at the left value and ends at the right value. This means it's a finite interval because it has a start and an end.
Your class periods are finite intervals. A chess match is a finite interval. Finite, beginning and end.
Lo and behold, there's something called an infinite interval. This is an interval that goes on and on and on and on, and we can't measure its length. When we have an interval that goes on and on and on, this is called infinity.
Infinity. So long. So very, very long. It's really long.
The symbol for infinity looks like a number 8 taking a nap. When we talk about infinity, we're usually talking about all numbers greater than or all numbers less than a certain number. Let's look how it's written, and then we'll see how it works on a number line.
When we see this, parentheses n, comma infinity parentheses, it translates into all numbers greater than n. It can also be written as this inequality: x is greater than n. While n stands for a particular number, that x stands for all numbers. So, we've got all numbers greater than n.
That's so many numbers.
Yep, it's a lot of numbers, but it's easy to deal with. All we gotta do is plug in a number value for n, then we can map it out on a number line. So let's substitute n with the number 4.
Now our interval looks like this: parentheses, 4, comma, infinity, parentheses. This means all numbers greater than 4. On our number line, we make an open circle at the number 4 and shade the line all the way to the right. Here the numbers start at 4 and go on and on. They never stop like they would in a finite interval.
Likewise, if we saw bracket 9, comma infinity, parentheses, this means all numbers greater than or equal to 9. We'd make a filled-in circle at 9 and shade all the way to the right.
What if you had something less than 0?
Well, if we have a problem where we're looking for all x's less than 0, we would write the interval notation like this. This symbol represents negative infinity. In the same way that positive infinity deals with the right-hand side of a number line, negative infinity deals with everything to the left side. For example, if we see this, this means all numbers less than n. N is just a stand-in for a particular number. We could choose a value for that number, let's say -1, and make it parentheses, negative infinity, comma, -1, parentheses. This means all numbers less than -1.
So, if we took the open interval of negative infinity to -1 and put it on a number line, it'd look like this. We've got an open circle at -1, and our line would be shaded all the way to the left. Now our number line represents all the numbers less than -1.
Now, we can even see something as seemingly cryptic as this. But don't worry, it's not Egyptian hieroglyphics. And unfortunately, it's not the recipe for world peace. It's not even the answer to a Final Jeopardy puzzle. But it is the interval that symbolizes all real numbers. Every last one.
To put it on a number line, we simply shade the whole thing all the way through both ends. This represents all real numbers.
So when we're talking about intervals with infinity, we have 5 basic combinations that we come across. Take a peek and see if you remember them all.
All real numbers. All numbers greater than n. All numbers greater than or equal to n. All numbers less than n. All numbers less than or equal to n.
Okay, just a little bit more about number lines and intervals. Back to our old friend, the absolute value. Remember that the absolute value of a number always equals the positive value of that number, or 0. Well, now we're going to put some absolute values on a number line.
Let's say we've got the absolute value of x is less than 3. In this case, we don't know what the value of x is, so our job is to figure out what number or numbers will fit correctly in our inequality if we substitute them in for x. Now, we do know that any value we choose for x has to have an absolute value that's less than 3. That's what our inequality says. So, what are some numbers whose absolute value is less than 3?
Well, any of the numbers from 0 to 3 work because their absolute values are all less than 3. For example, the absolute value of 2 is 2, which is less than 3. So it fits correctly. The same is true for all the numbers in this shaded area. Now, what about negative numbers? The numbers from 0 to negative 3 also work because their absolute values are less than 3. For example, negative 1 has an absolute value of 1, which is less than 3. That means it fits correctly. All the x values that satisfy our inequality can be found here in the interval between negative 3 and positive 3. Notice that we can't go any higher than positive 3 or any lower than negative 3 because any of these numbers will have absolute values that are greater than 3.
We can write the solution for our inequality in interval form, just like the others we've done. Parentheses negative 3, comma, positive 3, parentheses. Or we can write it like this. X is greater than negative 3 and less than positive 3. Both of these mean all numbers between negative 3 and positive 3, which are the numbers that satisfy our inequality. See how that all ties together?
Okay, say we've got the absolute value of x is less than or equal to positive 4. We know the lowest value we can possibly have for x would be negative 4, because anything beyond that has an absolute value greater than 4, and this would make our statement incorrect. See how the lowest we go is just the negative version of the number in our inequality. The highest we go is positive 4. So, our interval is bracket negative 4, comma, positive 4, bracket. And our breakdown looks like this. X is greater than or equal to negative 4 and less than or equal to positive 4. On the number line, we've got filled-in circles at negative 4 and positive 4, and we shade the line between them. All of these numbers satisfy our inequality.
Okay, now we're going to do one that's a little bit different. Our first two examples involved less than or equal to. But what if we had the absolute value of x is greater than 3?
Well, this tells us that the absolute value of whatever number x stands for has to be greater than 3. So any positive number greater than 3 will satisfy our inequality because its absolute value is greater than 3. But remember, we've got to figure out which negative numbers will have absolute values that are greater than positive 3 as well.
Well, all numbers less than negative 3 will work because their absolute values will be greater than positive 3. For example, if we pick negative 7, the absolute value of negative 7 is positive 7, which is greater than 3. Same thing with negative 138. The absolute value of negative 138 is positive 138, which is greater than 3.
So we've got two parts to our number line this time. We figured out that x can be greater than 3 and also less than negative 3. This means we've actually drawn the interval from negative 3 to negative infinity, and the interval from positive 3 to positive infinity, or x is less than negative 3, and x is greater than positive 3. These are the numbers that will satisfy our inequality.
I know it seems long, but once you do a few of these absolute value inequalities, you'll be breezing through them, and you'll want to do them for all your friends at birthday parties. So let's do one more to get the hang of it.
Say we've got the absolute value of x is greater than or equal to 1/2. We handle this one just like the last one we did. We know that we're going to have a two-part answer because of the greater than or equal to symbol. We know all the numbers from positive 1/2 to infinity will work because their absolute values will be greater than or equal to positive 1/2. But all the numbers from negative 1/2 to negative infinity will also work because their absolute values will also be greater than or equal to positive 1/2. So we've got the interval from negative 1/2 to negative infinity, or x is less than or equal to negative 1/2, and the interval from positive 1/2 to positive infinity, or x is greater than or equal to positive 1/2. These are the numbers that satisfy our inequality.
All right. We've reached the end of the number line circuit. Let's take a quick look back.
In Part 5, we've looked at putting inequalities and absolute values on a number line. With greater than or less than, we use an open circle at our number. But if we're talking about greater than or equal to, or less than or equal to, then we fill in our circle. Parentheses mean greater than or less than, and brackets mean greater than or equal to, or less than or equal to.
The sign for infinity looks like a number 8 napping. It can be positive or negative. Positive infinity deals with the right side of the number line, while negative infinity deals with the left. And if we see this, it means the set of all real numbers.
Remember, when we put absolute values on a number line, we've got to consider both the positive and negative versions. So, we'll always have two values, a positive value and a negative value.